In this tutorial, I will use the chemical machine to implement the concurrency primitives of the Go language. The Go programming language is supposedly very suitable for concurrent programming. And this is so because it has three primitives built into the language. One, the so-called goroutine. Goroutine is a method to start a function running on a new thread. The second primitive is channels. Channels can send and receive values, and in this way functions running on different threads, or so-called goroutines, can communicate. The third primitive is the select construction. The select construction is used to choose out of several channels one that can receive a value. In this tutorial, I will implement these constructions using the chemical machine, and we will see what the differences are between the methods of programming concurrent applications in Go language and in the chemical machine. The first construction is the goroutine, and this is quite easy. We just need to run a function on a different thread. We can implement this by creating a new molecule. Now, obviously in the chemical machine, there are no threads that you can control yourself. So in order to run something on a different thread, effectively what you need to do is you need to define a new molecule that will start some reaction, and you will emit this molecule. After you emit the molecule, the reaction will start automatically on a new thread. So the effect of a goroutine can be obtained if we create a new reaction and start it somehow. What would this reaction have to do? It will just have to evaluate our function. So suppose you have some function, such as this one, a pure side effect, as in the Go language. A molecule can carry that function as a value, and the reaction can be defined that will consume this molecule carrying the function f, and then it will call the function f on its empty argument, executing whatever side effects are there. All you would need to do then is to emit this molecule. Now, the interface of the Go language is that you say go, and then you say a function, whatever you want to be executed on a new thread. So to imitate that interface, let's define a helper method, goroutine, which will take an arbitrary value passed lazily, unevaluated. It will then prepare a function that will evaluate that lazy value and return unit, ignoring the lazy value. This function is put as a value on the molecule, goroutine emit. And so emitting this molecule will start this reaction. So let's check that this works. For each integer from 1 to 10, we will run a goroutine with this value of this function, which is going to be evaluated lazily. And this is the result. And you see that the functions are called in arbitrary order. So let's run this ourselves to see that this is so. 1, 3, 2, 4, 7, 6. And you see a different order now. So each time you run it, it will be maybe a different order. The second construction of the Go language is channels. A channel is an entity that has two methods, send and receive. Both are blocking. So you can send a value on a channel, and until somebody receives it, the send operation will block you. And you can also receive a value on a channel, and until somebody sends it, you are blocked on your receive. The simplest API that we can implement first is just that API. The Go language also has buffering, which we will handle next. So the channel with no buffering can be visualized as a pair of two requests, to send and to receive. Now in the chemical machine, obviously these must be molecules, because there's only one way to request anything concurrently, which is to emit a molecule. So we're going to have these two molecules emitted when we want to send or receive on a channel. Both molecules need to be blocking, since the Go language requires us to have blocking semantics on these method calls. So this will be our channel, and a function to make a channel will declare the send and receive molecules. It will declare a reaction that will consume these two molecules and reply the value x that you sent of type A to the receive molecule and reply an empty value to the send molecule. Let me just explain the syntax that we use to define reactions with blocking molecules. Blocking molecules are declared with two type parameters. The first type parameter is the type of the value that they carry, because blocking molecules carry a value just like non-blocking molecules do. The second type parameter is a type of the value they receive as a reply. The send request doesn't receive any value as a reply, it's just an empty value, so we use the unit type. The receive signal has a unit type for the value it carries, because we don't give any value for receiving, but it has the type A for the value it has as a reply value. In order to define a reaction with send and receive, we have two pattern variables in each of these two molecules on the left-hand side of the case expression. This is the syntax that Chymyst library implements. But when you emit these molecules, you don't have two parameters, you only have one. The other one is only for the left-hand side of the case expression. And the second parameter is the automatic continuation, which is the reply value. So this is a function that takes a reply value as an argument, and you have to call this function to call the continuation. Calling that function will unblock the thread that emitted this molecule. And so we need to call both of these functions. First, we unblock the thread that wants to receive, and then we unblock the thread that sent, signaling that we have successfully communicated. And then we return the GoChan structure, having these two molecule emitters as the parts of the case class. Let's test this code. We make a channel with integer values, and then we make two goroutines, as it would be done in the Go language. The first goroutine sends 10 values on the channel. The second goroutine receives anything that the channel has and prints the results. So let's run this. So this would be a typical pattern programming in the Go language. You run several things on the goroutines. One of them will send, another will receive. The Go language also implements buffering in channels. So you can specify that you can send on a channel up to a certain number of items of this type A, and you can send without being blocked. But once you send that many items, they are stored in some buffer. After that, any additional send will block until somebody starts consuming those elements that are buffered by receiving on that channel. That is the way that the Go language implements channels. Let's implement this now in the chemical machine. So we will implement this as a case class GoChan1. It's basically the same structure, except now we need to implement buffering. So how do we do that? Well, obviously we cannot just let send and receive interact directly, because that would be blocking. We need to have send reply immediately, as long as we have spaces in the buffer. Now we could use a data structure for a buffer, but such as a FIFO queue or some such data structure. But we won't, for simplicity. We just use molecules on the chemical machine. How do we do that? Well, clearly we need to have the values that somebody sent on a channel buffered somewhere. Now, the only way to store values on a chemical machine is to put those values on molecules. So let's have a molecule that will store those buffered values. Let's call it buffer. It's just a buffer for one element. Let's just call it buffer1 for clarity. It's a molecule that will store a single value that somebody sent. Now, how do we signal that we have space in the buffer? Well, we certainly could just say that send goes into buffer, but then every time somebody sends would create a buffer molecule. That's not good enough. So we need to prevent the send molecule from reacting if we have no space in the buffer. And we need to allow the send molecule to react and to get its reply when we do have space in the buffer. Now, having space in the buffer means that we have, let's say, available buffer molecules. But buffer molecules already carry values that somebody sent. They cannot themselves signal availability of a buffer. They signal that somebody already sent a value and it was buffered. So we need another molecule that signals availability of buffer places. Let's call this molecule ready. And if this molecule is present, it means we have a buffer place. So then let's make these two react. Send will react with ready and buffer its value into the buffer molecule, and then send the reply to send. So this will unblock the caller as long as buffer molecules are available. Therefore, if we want to model a buffer of size n, all we need to do is to emit n copies of the molecule ready. That will signal that there are n free spaces in the buffer. When somebody wants to receive, they receive from the buffer, and they signal that a buffer is ready. A buffer place is available, which is the ready molecule. Let's maybe rename this into available. And then it will be perhaps easier to read. So a receive request requires a buffer to be present with some value, and then the value is sent to the thread that wants to receive it, and the availability is signaled. The buffer molecule is consumed. It is not there anymore. So in this way, when somebody sends, first everything they send goes into buffer molecules until the available molecules are all consumed. And then any more send requests will just sit there and wait until more places are available. That's exactly the logic we want. So that's how this works. We can test this by making a channel with capacity 2 and then sending 2 values on it, and that should not get blocked because we have 2 spaces in the buffer. And then we do the same as we did in the previous test, and as you see when you run it, you will get everything sent and printed to the screen. So now if we make a mistake and send another value, then these 2 will be buffered, and this one has no space for buffering. And so this entire program will be blocked now. You see, nothing is printed. This is so because we're blocked. Our thread is blocked. So this is a deadlock. So just by sending one more time more than the buffer capacity, we achieve a deadlock. Let us also implement a channel with unlimited buffering. In other words, the send is non-blocking, and that's very easy in the chemical machine. We just declare send to be a non-blocking molecule, and the reaction is very simple. Send requests can be accumulated at will. They're non-blocking, so we don't need to put them into Goroutine anymore. Whereas here, we had these requests to send that were on our thread, and then the Goroutine. And because of deadlock, we never got to this point even. We never got to run anything that was receiving, and that's why we were deadlocked. But here the send requests are going to be non-blocking, and so you can have as many of them first sent, and then you can run a consumer to receive your values from the channel. So this works just as easily, and the code is actually simpler in the chemical machine. But this would be not easy to implement in the Go language, because the Go language requires you to have blocking APIs, blocking receive, blocking send. It takes extra work to make non-blocking send. The third construction that the Go language has is the select construction. This construction requires you to have several channels, and somebody will send on these channels. In the Go language, anyone can send on channels, just like in the chemical machine, anyone can emit molecules. So you see, sending values on a channel in the Go language is somewhat analogous to emitting molecules, although in the Go language it's always a blocking operation by default, and the channel must be buffered for some of the send requests to become non-blocking, as we have seen. The select construction will take several channels and receive from one of them, from whatever value could be available first on one of those channels. And each time you receive, you can do certain things with that value. And that is a blocking call. So select is a blocking construction in the Go language. So let's implement it. Let's just for simplicity make the send requests non-blocking, but we could have made them blocking just as well by putting the replies here and sending those replies, like I'm doing like this. We could do that, but let's not complicate the code. So here's how we could implement the select functionality. We declare a select molecule, which is blocking, and we declare reactions of the select molecule with every one of the send molecules of the channels. And each time, in each case, we can have different code. So just like in this Go language, where the select construction can have different code depending on which channel you received from, here we could have different code in each case. So let's test this. We will send from 3 different concurrently running or parallel running processes or goroutines. So this would be the typical Go language pattern. We will create these goroutines, send after a different delay, so they are all sent at different times, and then we would select several times. So each time will be a blocking call. And the output is like this. So the first time we select the first one that was sent, and the second time we select the second one that was sent, because this first one was already received. So the third one is not yet sent. So this is a construction that selects whatever is sent earliest. So let me run this and see that it prints what I expect. Yes. Now, the Go language also includes a default clause in the select. In other words, if no values are available on your channels, then there's a default clause that is executed then. Let's model this in the chemical machine. To do that, let's introduce a molecule which will react with select so that we can write a default clause, just like we wrote these 3 select clauses. Let's do it like that, very similarly. And now the question is, who is going to emit this molecule and when? So we can run the test just like we did before. But now we are faced with the question of who is going to emit this molecule? Well, we must emit it. Certainly the third-party code that could be sending to us doesn't know about this molecule. We must emit it, but when? And in this way, we are alerted immediately to the problem in this construction, which is that it is unreliable. Depending on when we emit the default select molecule, the results of this could be different. It could time out, so to speak, at different times. So in this test, the result is like this. It defaults, but after receiving the first one. Now, clearly, this might be reasonable in some applications to have this behavior, but notice here we have very specific values that we wait before sending. In a typical application, the send would be unpredictable. We don't know when some processes that run in parallel decide to emit their signals. And so the default clause will sometimes fire and sometimes not fire, depending on unpredictable circumstances. So it's a timeout functionality, really, rather than a default clause. It is misleading to think about it as a default clause, because, as you see, everything depends on timing. It's really a timeout clause. Now, the timeout functionality is certainly very useful in many cases. And this is how you would implement it. However, the timeout functionality still is not exactly very reliable. this timeout could get too late. You don't really know what timeout to set. It's always a heuristic value. Programming in the chemical machine alerts you to this directly. So this is a problem. This is a potential unreliability in your code, and you need to think about it. Whereas the Go language pretends that this is just a default clause that somehow just works, and that is misleading. It is a timeout clause, and as we know, all timeouts that we just set by hand to some reasonable values are actually unreliable and brittle. Another difference between the the chemical machine, I wish I had a time machine, and the Go language select construction is that the Go language construction can be introduced at any place in the code after the channels are defined. This is not possible, however, in the chemical machine. And let us see why. Let's try to do this, and the chemical machine will generate an error. So let's just use the GoChan definition of our previous example and make a channel, make another channel, and then try to define the select construction with those channel send signals as before. And the result is that the chemical machine gives you an error. The error is that you cannot redefine the chemistry. I prefer to talk about it in this manner. The actual message is the molecule cannot be used as input because it's already bound to another reaction site. So the molecule send, which is the channel send of this, is already bound to the reaction site defined in the channel. It cannot be bound to a new reaction site because that would amount to changing the chemical laws of that molecule, the chemical laws that define what this molecule reacts with. Once you have defined the reaction site, you have fixed all the other molecules that a given molecule reacts with. You cannot later add new molecules that it also should react with. You cannot add new chemical laws for the same molecules as input. And that is what it tells you. The molecule cannot be used as input in this site, select, send, which is obviously this site, because it's already bound in site receive and send, which is the channel site. And the channel site is defined inside this function. So this is an important difference. The chemical machine enforces the immutability of the chemical laws, so to speak, immutability of reaction sites and reactions. The result is that once you have defined your reaction site, say in some library, so imagine that this make_chan resides in a library and you're using that library. Now that library wants to make sure that its chemical laws remain immutable. And that's why the chemical machine enforces this rule. So make_chan in the library already defines that the send molecule reacts with a certain molecule. So you cannot later add another molecule that it reacts with. But in the Go language you can. You can say that, oh, now I'm also reacting with that signal. And at some other later point in your program, you can add more of those. The result is that you don't know what is waiting on your channel. You don't know who is going to consume your messages. Anybody at any time can consume your messages. So you cannot make a library that reliably designs a certain logic of who is sending and who is consuming. because at any time anybody could consume more and take your message out of your hands, or take your molecule out of your hands. The chemical machine prevents that. And so you can reliably design logic by reasoning about molecules, and you know that nobody could consume your molecules from under you, so to speak. So in the Go language, the logic of who listens on channels, who receives data from channels, is completely dynamic, whereas in the chemical machine it is static. It is defined at compile time. Once you have a molecule, there's one place in the code where it is defined what other molecules it reacts with. You can find that place in the code, and nothing else, no further code could possibly change that. That is the guarantee of the chemical machine, the static immutability of chemistry. And this is not the case for the Go language. So it would be, strictly speaking, impossible to implement a select method for the chemical machine in the same way as it is used in the Go language, by taking these channels and redefining the chemistry or the reactions that these molecules already have by adding another set of reactions with a new molecule. So that is impossible. Certainly you can reproduce the same logic in a different way. So you can do it like we did here, where we already define the channel logic at the same time as the select logic, but you cannot do it in the way that the Go language does it, because the chemical machine gives you stronger static guarantees than the Go language. Let us consider an example that is presented in a talk. It was presented in this talk, Advanced Concurrency Patterns in the Go language. Where they considered this ping-pong game. The program in the Go language looks like this. It defines a ball structure, which is counting the number of hits. Then it defines a channel called table. Then it initializes two players, ping and pong. Each player does the same thing. It receives the message from the table channel, and the message is the ball, increments the hits, it prints a message, sleeps for 100 milliseconds, and then it sends the new changed value of the ball back to the table channel. Each player does this. So we have two players, and then we put a ball message into the table channel, and then we sleep a little, and then we grab the message back from the table channel, which will stop the game, because there will be no more message, and none of them will be able to do anything. So they will both halt indefinitely. That is the code that I directly copied from the slide in this URL. So now I'm going to copy this code basically line by line using my goroutine and channel definitions that I just showed you. So it's going to be this code. It's slightly shorter, but it's only because of formatting. It's exactly the same code. I have an integer counter. I make the channel say exactly the same thing. I make the channel. I run the two goroutines with the player. Then I send 0. The new ball is 0. I sleep 1000 and I receive, which is exactly this. And the player is defined in exactly the same way. It's a while true. Receive from the table, increment the value, print message, sleep, send to the table. Exactly the same code. I run it and it works. However, sometimes the ping starts the game and sometimes the pong starts the game. Why is this? Well, it's because nothing in this code actually says who should start the game. We started the first goroutine as ping, but this doesn't actually guarantee that it will be the ping thread that first receives from the table channel. Both of these receive from the table channel at the same time, and so they contend on messages on that channel. And so this is a non-deterministic program. Let's implement the same functionality, but using more idiomatic chemical machine code rather than just translating from the Go language. So we won't be using any goroutines, we just use straightforward reactions and molecules. How would we do that? What we need to implement is that we would like a chosen player, either ping or pong, to start the game. We again want to count the moves and print messages. And we want to have a blocking signal, such as stop, that will stop the game, just like in this initial implementation. To do that, obviously, we need to represent the count of moves, and we need to represent which player has the ball now. This information in the chemical machine obviously needs to be put on some molecules, otherwise nothing works on the chemical machine except if you take molecules. So define ball with integer value, so that would be the counter, and define side, which is a molecule that carries the current player's name. This is the information we need to represent. So in the chemical machine paradigm, we start from the data. What is the data that needs to be handled by concurrent processes? So this is the data, the play count, and the current player's name. And also we want a blocking signal stop, and let's make that signal return the number of moves played. So the type of the value that it carries will be unit, and the type of the value it returns will be int. So then let's define reactions. So reactions are clearly, you need the ball to react with something. So let's see how we can do that. The ball can react with the side and emit a new ball and a new side. So that's an obvious thing to do because we need to update the move counter and the name of the current player. So we need to consume the molecules that currently carry this data and emit molecules that carry the updated data. So let's put that into a function. And we'll do that. And this function prints the message, waits, computes the name of the next player. Just for simplicity, let me do it in this way. And then we emit the new ball with updated value, which is updated because we already have it here, and the new name. And the reaction for stopping is that when the stop molecule is emitted, it will react with the ball and absorb the ball. So after this reaction, the reply is sent. We obtain the number of moves played, but there is no more ball molecule emitted. And so the game will stop, clearly, because there is nothing more to do. So in this way, we implement the game. So we specify which side is first, we specify what is the initial move, and then we sleep for some time and stop the game Now, this is a blocking call, which will not return until we actually have stopped the game. And to verify that, we sleep for some more time to see that nothing else is printed. So let's run this and see how well that works. So we have actually played a bit more than we thought. We would expect to play 10 moves or so, because we're waiting for 1 second. But actually, we had to wait almost 2 seconds, so obviously this is not very reliable. It does stop, but it just takes a bit more time than we thought. So let's try to optimize this. So how can we do that? I mean, this is correct, but just not very efficient. Let's optimize that with more reliable stopping. How do we do that? So let's think about it. Let's actually include the stopping logic into the play. And we'll do that by putting, instead of a side name, ping or pong, we'll put the name stop. And we'll insert the stop command, so to speak, right there, rather than have this logic where the two reactions compete for the ball molecule. So clearly the problem is that the two reactions compete for the ball molecule, and so this reaction is selected rather than this one. Even though the stop molecule is available, eventually this reaction is selected, but not quickly enough. So we want right away, right here, we want to insert a different molecule side with a different value. So then there won't be a contention between two reactions for the same molecule. So that actually works more reliably. To do that, we modify the logic so that if the name here is stop, then we don't emit a new ball and a new side. We emit a special molecule called stopped that carries the value we want. And then we define a second reaction that consumes stopped and our stop signal. And then it replies with the value n. Other than that, the logic remains the same. And we also, now in order to stop, we need to do two things. We need to emit a molecule side with value stop and emit the stop signal. So we have now a method for stopping, which is like this, very simple. And we have the new test code. Let me run it. And it is quite reliable. It always finishes at the same point. So the difference between these two things is that in this chemistry there is no contention on molecules. There's no question of which reaction to run. There's always these two molecules or these two. And the side molecules are certainly emitted one after another. And so it's much less contention in that situation. Once we emit a new ball molecule, it can react with the next side molecule right away. And there's much less time that needs to be spent in this implementation to select a new reaction. There's no contention on molecules. So this concludes the tutorial examples, and let me just make some comments about the differences between the chemical machine and the Go language. So as we have seen, we can implement the Goroutine, we can implement channels, and we can implement the select construction. Now, there are very important differences between how channels work in the Go language and in the chemical machine. Namely, in the Go language, everything is blocking by default. In the chemical machine, everything is non-blocking by default. And as a result of this, we have seen the chemical machine makes it much more apparent that certain logic is non-deterministic. For instance, in the implementation of the default clause in the select, we have seen right away that there is a problem with non-determinism, whereas in the Go language, it's not apparent. Also, as we have seen, the Go language is much more dynamic, that is, checking less about who is receiving messages. It's very easy to receive messages from any channel, from any place, but the logic of concurrent applications usually depends on having data or not having data, or having a message or not having a message. So being able to consume a message in any place in the code, in user code and library code, in the code written later, makes the logic very convoluted. It's much harder to understand who can consume a certain message in the Go language than it is to understand in the chemical machine which reaction may consume a certain molecule. And in the chemical machine, reactions are determined statically, whereas in the Go language, the logic of who is consuming what messages and who is sending what messages can be spread out through large code base and modified by later user code. So you cannot very well encapsulate such logic in a library in the Go language, but you can in the chemical machine. You can have very reliable libraries of chemical machine code that encapsulate new molecules and new reactions with no possibility of modifying this logic by any later user code. So these are the main similarities and differences between the chemical machine and the Go language.